Okay, we're going to work with numbers, and as such, we need to classify numbers. I'm going to give you a little bit of an algebraic story of how numbers came about. This is not a historical story, but rather an algebraic story. So first we have the set of natural numbers, which is denoted with an n and a double bar to the left. And this is the set of numbers 1, 2, 3, 4, 5, etc. So all of those numbers with no ending, because there's no end to it. If you get to a million, you can always add one more, 1,000,001. Once you get to a billion, you can add one more, and so forth. So there's no end to these numbers. There's a first number, which is the number 1 of the natural numbers. So this is the set of natural numbers. That's it. And this is good enough for counting. You know, do you have $5 or 3/4 or 2 chairs, 1 desk, 1 telephone, etc. So this is good enough for counting. And it is good enough for solving some equations. So for instance, 4 plus x equals 9. This equation can be solved within this set. Of course, the answer is 5. And then everybody's happy as long as we have this kind of equations to solve. The problem comes up if we have an equation such as this one, 4 plus x equals 1. We cannot solve this equation within this set. You know, you try, any number you plug in for x will cause the addition of 4 plus that number to be more than 4. And 1 is a lot less than 4. So we cannot solve this equation. So this one we are able to solve. This one we cannot solve within this set. So what we can do is expand this set into a new set, which we will denote with a z and a double bar here. And that is the set of integers. So let me name this. These are the natural numbers. Okay. And the set of integers will contain 1, 2, 3, etc. without ending the set. And we will have 0 as well as -1, -2, and so forth without ending on the other side. So we have non-ending on the right and non-ending on the left, and 0 sort of in the middle. And notice that we added a new symbol, this negative symbol, which differentiates the numbers from the numbers on the right of the 0 versus on the left of the 0. So now we have negative numbers, and now we call those positive numbers. See, in this set, there was no need to call anything positive because there was only positive numbers. But now that we include a separate set besides those numbers, the original numbers, now we label those as negative, those as positive, and 0 is neither positive nor negative. So now we are able to solve this equation, 4 plus x equals 9, rather 4 plus x equals 1. I was copying the equation, the first equation, but of course that was solvable in the first set. So 4 plus x equals 1 now has a solution. Of course, the solution is -5. And now we are very, very happy with this set. People were very happy with this set because we were able to do a lot of things with it. But eventually, somebody, again, this is a story, a made-up story of how the numbers came about. And I just happen to like this story. I heard this story a while ago in the 70s. I honestly forgot who told me the story, but it is an interesting story. And somebody came up with this equation. Hey, let's try to solve this equation. 4x equals 3. And no matter what number you plug into 4x, in this set, we cannot solve this equation. 4 times 1, well, that's going to be 4, so that's not 3. We need a 3. We need a 3 here. 4 times 2 is 8. Well, that's way above 3. And 4 times 3 is 12. So any number, even 1 for x, will cause the left side of this equation to be greater than 3. So this is not going to work for any of those numbers. If we multiply with a negative number, 4 times a negative number is going to end up with a negative number, but this number is positive. So we cannot solve the equation with negative numbers, with positive numbers. If we plug in 0, 4 times 0 is 0. So we can't solve. So if we have this set, there are some equations that cannot be solved. Just like up here, this set was good for counting, but then eventually we were not able to solve this kind of equation. Now that we are able to solve this equation, there's a new equation that we cannot solve anymore. Isn't that interesting? So people thought about how to solve this problem of solving this equation. I mean, think about this from a developmental point of view. At some point we had to come up with numbers that were able to solve this equation. So, and at one point there wasn't, or there weren't any. So we came up with, or the math people came up with, this set. It's a Q with a double bar on the left, and that is the set of rational numbers. I missed to mention what those numbers are. So this is the set of integers. So we just name them integers. There we go. So now we got this set. This set is a lot more difficult to write term by term or element by element. Here we're able to write some elements, and then we use the ellipsis to tell that this set continues in the same way without ending, and same thing here. But with rational numbers, it is way much more difficult to do that. We would have to make a huge table. So this is the set of all the numbers that can be written as fractions. So A over B, such that A and B are integers, with B not equal to 0. Okay. So this is the way we describe. So in this case, we have to describe the set as opposed to write down each one of the elements. When we are describing a set, you can actually write down the elements in the set. So for instance, if you write down the set of the people who live in your household, well, it could be just yourself, or it could be a couple, a few people. There are only so many people who live in your household. But if you want to represent the set of all the males in the world or all the females in the world, well, that set is going to be huge. But just as well just write it as the set of, in words, all the females in the world or all the males in the world. And then it is understood what kind of set we have. So this is what we have to do in this case. There are so many different kinds of fractions that writing the set this way is way too difficult. It is not impossible, I think, but it is way easier to just describe the set with words. So that's what we do. Now, notice that I said the set of all the numbers that can be written in this way. Yeah. I'm going to come back to that in a little bit, but that is important. I didn't say all the numbers that are written in this form, but that could be written in this way. There's a couple words I have to say about that. But anyway, so some examples of this kind of numbers are like 3/4, negative 7/8, 2/15, etc. 99s. Yeah. Notice that there is a complication. There's a few complications actually with this. Um, a number may be written in more than one way. So 99s can be written as, well, 33rds, which can be written as, well, 10. Yep. So all of those numbers represent, all of these expressions, 90 divided by 9, 30 over 3, 10, all of them represent the same, even 10 over 1. So we have a complication. The complication is that now we may write a number in more than one way. We did not have that issue here necessarily. Although somebody could argue, well, 3 can be written as 1 plus 2. Yes, but generally speaking, we quickly simplify that into 3. And here, there's many, many more ways to write fractions. Anyway, 0, by the way, is another example of a rational number. So this is the set of rational numbers. So set of rational numbers. And now we are able to solve this equation. 4x equals 3. No problem. 4x equals 3 has a solution. In fact, the solution is the first example I gave, 3/4. So 3 over 4. When you multiply 3 over 4 by 4, sure enough, we end up with 3. So now we are very happy. We are able to solve this equation. A lot of people were very, very satisfied with rational numbers. And everybody was happy for a while until somebody came back and said, wait a minute, there's an equation I want to solve, and I'm not able to solve it. And the equation was x squared equals 3. Again, this is a made-up story. I want to emphasize that. So, boy, no matter what fraction you put in here, for x, there's no way that we are able to solve this equation exactly. There's no way. And the reason is because if you write the fraction in simplified form, when you multiply both sides of the equation by the denominator, there's an extra 3 on this side that wouldn't happen on the other side. Because of the squaring, that means that we're going to have pairs of numbers like 2 3s or 2 5s or 2 7s. So eventually we end up with an extra 3 that doesn't work. Anyway, we cannot solve this equation. So now let's put an unhappy face. We cannot solve this equation with a set of rational numbers. So along this, we have had the same kind of problem. First, we started with natural numbers. Yeah, we're okay with this kind of equation. Modify the equation a little bit, and we cannot solve the equation with that number. With those numbers, that set was not sufficient. We extended the set to this, to the negative numbers and 0, and now we are able to solve that equation. But now we cannot solve this equation, so we go through the same thing again. We extend the set of integers into the rational numbers. By the way, every time we are doing this, we are extending the set. The natural numbers are part of the integers. The integers are part of the rational numbers. So we have to do things very carefully because things have to be consistent as we go from one set to the next set. And now we have a new problem. We cannot solve this simple equation with the set of rational numbers. So again, people thought about it, and they came up with the set of real numbers. So we use the letter R with a double bar at the beginning. So Again, there are way too many. This was already way too many to express with a list of numbers, even if we use ellipses. So we describe the set of real numbers as the set of numbers that correspond to points on a number line. So I'm going to describe this with a number line, and then we have 0 and 1 and 2 and so forth, and -1 and -2. All right. Now, there is all the fractions in between, but in addition to the fractions, there are more points that are not fractions. Well, the set of every single one of the points on the number line is the set of real numbers. So we're going to describe the set of real numbers as the set of all the points, every one of the points on the number line. Now, this number line has no end to it. This arrow indicates that it keeps going on, and so that's on the left. So there is no end point, and there is tons and tons of numbers in here. So this is the set of real numbers. And now we can solve this equation. X squared equals 3 has a solution, has a real solution. And the solution is square root of 3. Actually, there's more than one solution because negative square root of 3 also works, and opposite of the square root of 3. So square root of 3 is somewhere between 1 and 2. Let's just say here is the square root of 3. But then there is another solution somewhere on the left. Yep, negative square root of 3. There's actually two solutions to that equation, to this equation. So people were very happy with this. They thought they were all done and finished with this set. This was a very satisfying set because we are able to solve many solutions. And even if we are not able to come up with the exact answer, we can always approximate the answer. So people were extremely satisfied with this set until somebody came up with a new equation, a very simple equation, which cannot be solved with that set. So we had to do this extension again. So the new equation, so this is good. The new equation is x squared plus 1 equals 0. Very simple equation, which cannot be solved with real numbers. And the reason is because every time you square a real number, invariably the answer will not be negative. It will be either 0 or positive when we square any number. So even if you have negative square root of 3, if we square that quantity, you end up with positive 3, a positive number, or the least that we can obtain is 0. Well, that means that the left side of this equation has to be at least 1. And there's no way we can get down to 0, all the way down to 0 in this equation. This equation will not work, no matter what input we use, as long as it is a real number. It won't work. So again, people have to go back to work and try to think, okay, so how can we solve this equation? And the answer is, eventually people came up with a new set, which is the set of complex numbers. Yeah. Again, this set is way too large and too difficult to list, but we can describe what it is. It is the set of all the numbers which may be written in the form a plus ib or bi, okay, such that a and b are real numbers and I is the imaginary unit so that I squared equals -1. Okay, so this is a rather long description. So for instance, examples of a complex numbers are 3 plus 2i, for instance, or 7i, or actually just 8 is a complex number, or I by itself, or -I, etc. All right. So with this set, we are able to solve this equation. X squared plus 1 equals 0 has two solutions, just like this one has two solutions, square root of 3 and negative square root of 3. This one has solutions I and opposite of I. So there are two solutions for this equation. And now we are able to solve every equation, every algebraic equation that we can come up with. So this set is the best set we can come up with because it is able to solve all of these equations. And in addition to that, it contains the natural numbers, which are contained in the integers, which are contained in the rational numbers, which are contained in the real numbers, in the set of real numbers, which are contained, again, in the set of complex numbers. So this set is very, very satisfactory. We can solve any algebraic equation, I mean, any one we're able to. Now, how do we go about solving equations is a different matter. Some equations are extremely difficult to be solved, but nonetheless, we are able to solve them no matter what. There are other sets that we should consider. Again, we have to become very familiar with the kinds of numbers we have at our disposal because we're studying mathematics. And so when we study anything, whether it is biology or chemistry, we start classifying things so we can name them. Otherwise, we're going to describe everything, the numbers 1, 2, 3, 4, 5, instead of just saying the natural numbers. Is much easier to use a name for the things that we are working on. So other kinds of sets, or other sets rather, sets of numbers, I include this set of prime numbers. Okay, so prime numbers. I don't think there is a particular letter for them. Some people may use a pi, but let's just call them prime numbers without a specific letter for them. So the smallest prime number is 2. The next one up is 3. The next one is 5. The next one will be 7. So here, this is one way to come up with those numbers. So start with 2. And if the next number is not a multiple of 2, then that's our prime number, 3. If the next number is not a multiple of 2 or 3, then that's a prime number. But 4 is a multiple of 2. It's 2 times 2. So that's not a prime number. So 5 is not a multiple of 2 or 3. So that is our next prime number. 6. So the way we do this is by steps. You move up to the next number. If the next number is a multiple of the previous prime numbers, established prime numbers, then that is not a prime number. So 6 is a multiple of 2 and a multiple of 3, but it's enough just to be a multiple of one of the two. So 6 is not a prime. 7 is not a multiple of any of the ones before 7. So that means that is a prime number. 8 is a multiple of 2. 2 times 2 times 2 is 8. So that is not a prime number. 9 is a multiple of 3. 3 times 3 is 9. So that is not a prime number. 10 is not a prime number because it is a multiple of 2 and 5. 11 is the next prime number. And we can continue this list without ending. So the prime numbers are a subset of natural numbers. Prime numbers are natural numbers. But natural numbers are not prime numbers. So we got to be careful with that. We have the set of even numbers. Even numbers are, you probably are familiar with that, 2, 4, 6, 8, and so forth. But then we also have 0, -2, -4, and so forth. So those are the set of even numbers. So a number is even if 2 times x equals, let's say 10, as long as this guy is an integer, then we have an even number. So again, 2 times an integer equals 10 means that 10 is an even number. So if a number is 2 times an integer, then that number is even. You see, things can get a little tricky because we have to be able to tell when a number is even and when a number is prime or not prime. Yeah, prime numbers are very important. We have the set of composite numbers or composite numbers. Essentially, they are the ones that are not prime, but we start with 4. So the ones we skipped here are the composite numbers, so 4, 6. What else? What was, so 4 was missing, 6, 8, 9, 10, 8, 9, 10, 12, and so forth. Those are the composite numbers or composite numbers. Oh, we got to talk about decimals. Very, very important thing about decimals. All right, so decimals. Okay, so a decimal is something you're familiar with a decimal such as 0.333, etc. forever. So they use this symbol, a little bar on top of the last digit, indicating that the 3 repeats. We will not, I repeat, we will not use infinite decimals in my classes. So no infinite decimals. No infinite decimals. If you write an answer and it is an infinite decimal, this is considered an infinite decimal, I will more likely than not take points off. So please be sure not to write infinite decimals. No infinite decimals in this class. I'm not totally against them, but I feel we miss the concept of the development of numbers if we use infinite decimals. There's a couple of reasons why. That is one reason why I prefer not to use them. So don't use that. Oh, the other thing is, okay, so where does that come from? This could come from dividing 1 by 3. If you divide by 1 by 3, there is your 0.33333 forever. The question is, what happens when we multiply this infinite decimal by 3? So if you do 0.333 forever, and you multiply by 3 again, well, you end up with, well, 3 times 3 is 9, and that happened for all the other 3's. past this one, and then 9, so there's a bar on top of that, and then 9 again. 9 times 3 is 3. There's nothing to carry over. So we end up with 0.99999. But in reality, if you have 1/3 and you multiply by 3, we're using this middle point as a product, then we of course know that the 3 simplify. 3 divided by 3, or let's just do this differently. This is 1 over 3 times 3 over 1, which is 3 divided by 3, which of course is the number 1. It is true that this infinite decimal 0.999999 forever is equal to 1, but yeah, we want to avoid this. Becomes a little bit ambiguous. Not ambiguous. It is clear that this is equal to that, but it gets a little confusing. So to avoid all of that altogether, we will not use infinite decimals in this class, in any of my classes for that matter. Please avoid infinite decimals. They are a little more confusing than what we wanting them to be. And the other reason why we don't want to use infinite decimals is because then we would be talking about infinite series, an infinite series. And we haven't really spoken about infinite series in this class either. So there's a couple reasons why we won't use infinite decimals in this class. Now, what they say about infinite decimals, a rational number is a decimal that repeats, has a sequence that repeats. All of that is true. And irrational numbers do not repeat, and they have infinite decimals and so forth. All of that is true. So I'm not negating any of the things that other books tell about infinite decimals. I'm not stating that that is wrong. I'm just saying in this class, we won't use infinite decimals. We will use either terminating decimals or fractions, or simply so if you want to write square root of 3, just keep it a square root of 3. Unless I ask you to find a decimal and to approximate it, don't use a decimal. Same thing with 1/3. Don't use a decimal, or 2/7. Don't use a decimal. Now, there are some cases where a decimal would be okay. So 1/5 is okay because that is 0.2. It terminates. There's no infinite decimal. Although, technically speaking, one could say, well, there's an infinite number of zeros past the 2, and that is true. So what we mean by an infinite decimal is a decimal for which other than zeros, eventually we have other things that are other digits than 0 after, forever. That's what we mean by an infinite decimal. So this is not what we call an infinite decimal. This is a terminating decimal. So this is okay. Either way is fine. Okay. The other thing I want to state is we always write the simplest form of a number. So we always write simplest form of a number. So for instance, if you have 100 over 20, well, the simplest form would be 5. Yeah, we don't want to write any other form but that one. That is the simplest form. If you write any form that is not the simplest, then you will lose a point probably, because answers have to be as simple as possible. So no infinite decimals, unless, no, we won't use infinite decimals. If we want a decimal as an answer, then we have to write down either a finite decimal as that one, or we would have to approximate it with rounding. Just a quick thing about rounding, of course. if we are rounding after 3 digits, or 3 digits after the decimal point. So if you have 493, for instance, this gets rounded to, well, we need one more, 2 there. If we want to round to 3 decimals after the decimal point, then this 2 disappears. Then we end up with 0.493. Yep. Yep. And I think that's all we have to say about sets of numbers for now. So we'll stop the recording right now.